In this video, we'll be presenting Embodied Axes, tangible actuated interaction for 3D augmented reality data spaces. Modern immersive environments, such as virtual and augmented reality, offer true stereoscopic environments and the ability to engage directly with the 3D visualizations. Most AR and VR environments allow us to walk around 3D virtual objects, peer around them, and grab them with our hands or with tracked controllers. While this input style allows engaging in more natural interaction, there are inherent issues to using our hands or track controllers for data visualization purposes. For example, there are the lack of affordances. It can be a fatiguing interaction, and it can be rather imprecise. Our arms and hands jitter and prevent detailed interaction, for example, selecting a point or precise value along a visualization axis. There is a momentum for medical practitioners to put their data into virtual or augmented reality. The operations that radiologists or general practitioners perform with 3D imaging requires precise interactions such as slicing or selecting 3D regions. This has been studied in previous work such as Sosa et al., but using 2D surfaces as input to support 3D medical imaging. In this work, we introduce a more natural 3D interactive mapping to support these operations in immersive environments. We present Embodied Axes, a device for making precise selections in three-dimensional visualizations. So the device is designed to be used with an augmented reality head-mounted display such as the Meta 2 pictured here. The AI display provides the immersive visualization of the data, while the user input is performed with the embodied axes. When designing the embodied axes, our aim was to provide a coherent environment in which you can still naturally interact with your hands, while supported by the tangibility of physical affordances for precise selection. To achieve this, we had a set of design goals and principles that drove development. First, we wanted to support a set of common data tasks that occur in 3D space, such as filtering and selection. Second, we wanted to support precise selection, as we found that was what is expected from our experts based on the interviews we've had. We also wanted to provide a physical frame of reference for these tasks, which is enabled through tangibility. And finally, we realized that multimodal input was essential to supporting both precision and the fluid interaction available from our hands. The embodied axes physically embodies a three-dimensional data visualization space. It provides this physical 3D frame of reference with three axes for the X, Y, Z dimensions. Each axis has a range slider composed of two physical sliders, and these sliders are actuated so they can actually move by themselves. Each axis also features a rotary button. The sliders afford direct, tangible, and precise input. The actuation supports coordinating the user's hand position with the configuration of visualization if needed, so there can be this feedback loop between the input and the output. The actuation also supports haptic encodings, potentially allowing the user to feel the data they are examining. The result is coordinated gestures supported by physical affordances to explore and examine data. This is known as spatio-data coordination. A user of the device can independently set for each axis single values using the position of a single slider, range values using the position of both sliders on the same axis, fixed range values by using the actuation of a single slider that follows another slider, and delta rotation values using the rotary button that can represent deltas or continuous values. The user can slice data along a single dimension with one slider, or select a slice range using both sliders on an axis. The actuation can set the sliders to follow each other at a fixed distance, creating a fixed range selection. To explore remote collaboration between two users, we replicated the Embodied Axes prototype device and created a network layer. We tested this setup between two Australian cities, and we observed that the device can potentially provide a valuable cue for increasing the sense of presence of the remote collaborator. We also explored integrating the embodied axes with several input modalities. Here we illustrate the natural hand tracking integration with the Leap motion controller. So with this configuration, the user can use a rubber band interaction between their tracked fingers to select a volume. The actuated sliders reflect the volume and can be used to fine-tune the selection along the axis. The embodied axes can be used in the context of abstract data visualization. So for range selections, value filtering and volume selection are all supported in this context. The rotary dial can also be used to map the data dimensions to specific axes. We ran a formative study with 3 medical practitioners, a radiologist, a forensics expert, and a 3D medical imagery engineer. And in this study, we explored their common tasks involving 3D visualization and interaction, and we explored how embodied axes can support these tasks. So we received positive feedback on its ease of use, the intuitiveness and the tangibility for precise selection, and the experts suggested that embodied axes could be used to measure regions in the 3D data, or the actuated sliders could even track a needle in the 3D volume. They also identified the need to be able to rotate the 3D object while keeping their 3D frame of reference. This formative study eventually informed the tasks that we ran in the follow-up controlled user study. To assess the performance that users can achieve with the embodied axes, we conducted a controlled user study. We compared the embodied axes to state-of-the-art 6DoF track controllers in an augmented reality environment. In this study, we tested 3 tasks: target selection, volume slicing, and 3D bounding box selection. These tasks were informed by the formative user study with domain experts. For the target task, the user had to match the value and position of the grey target with the red target. For the slice finding task, they had to find the center of the biggest sphere hidden within a 3D volume. And for the bounding box, they had to define the smallest bounding box around the red dots in the 3D scatter plots. With the track controllers, participants manipulated the targets and the volume directly with the motion controller. In the embodied axes condition, they had to move each slider knob. We found that for precise selection, participants were 56% faster with embodied axes and were more precise. For the bounding box task, we found a trade-off between time and accuracy. People did more casual selections with the track controllers. For the volume browsing, or the slicing task, we found no difference between the embodied axes and the track controllers, but we did find that the embodied axes may be preferable for extended use due to less fatigue based on our post-study survey. More information about these results can be found in the paper. So to wrap up, we presented embodied axes as a new controller to interact with 3D immersive visualizations, and we demonstrated the application of this controller in the context of the medical practitioner domain. We identified a set of novel interactions that use the motorized slider that are part of the design of the embodied axes, and we compared it to state-of-the-art 6DoF controllers and found clear advantages for using embodied axes for particular selection tasks. For future work, we need to support more interactions, so things like scaling and rotating, essentially everything that breaks the frame of reference that we've established. We also need to explore collaborative use cases, as the domain experts found this to be a particularly compelling use case for the technology. And again, for more details or questions and follow-ups, please look into our paper.